Okay, so we again start with a new lecture. Let me just recap the last lecture. In the last lecture, we learnt about just one second, materials tetrahedron, and basically this was about, you can make a tetrahedron like this, and on one hand you have properties of materials, on another hand you have applications, on this side you have structure, and then you have processing. Now, processing is very important here because processing affects the structure, especially the microstructure, and structure affects the properties, okay, a microstructure and nanostructure. Crystal structure is normally something which does not change significantly until you do some special kind of processing like non-equilibrium processing. So, under most processing methods the crystal structures does not alter, the phase fractions may alter, and the microstructure may alter, which will give rise to change in the properties, and that will affect the applicability of the material. So, this is how these things are related. Processing is also related to applications because processing is related to cost and ease of processing and manufacturability. So, this tetrahedron basically shows you interrelation between four important aspects of materials engineering. And then we discussed about classification of materials. So, classification of materials was basically in four categories: metals and their alloys, ceramics, polymers, or let us say plastics, polymers and elastomers, and then we had hybrids. Okay. Now, these are basically on the basis of type of materials, in the sense that metals are strong and ductile, and they have high electrical and thermal conductivity, but they are not very good, they do not have good corrosion resistance. Ceramics on the other hand have very high strength, but they have very poor ductility, they are very brittle, they have low coefficient of thermal expansion and poor electrical and thermal conductivity. Plastics are ductile, they can be stretched to long lengths, they also have good toughness, they have corrosion resistance, but their high temperature properties are suspect, and hybrids are something which you intentionally make. So, this classification of materials basically is not only because of properties, but properties are because of structure and bonding. So, this classification, the basis behind this lies in structure and bonding. As we will see, metals are metallically bonded, and because of bonding they are malleable and ductile. Most ceramics are ionically and covalently bonded, that is why ceramics are hard and brittle and strong. Plastics are a mix of covalent bonding and secondary bonding of van der Waals bonding, and that is why they are softer. And hybrids are mixture of both of them, so they may have a different scenario, but this particular classification of these three categories is primarily related to the bonding in materials. And then we looked at the scale of structure. So, when we talk about structure has various scales. So, first scale is the macro, second is micro, third is nano, fourth is atomic. Now, it is so in the context of materials engineering, we are interested in microstructure, which is the structure and distribution of phases, grains, grain boundary, etc., impurities, inclusions at micron level or submicron level scale. Nanostructure could be again related to same as microstructure, the formation of nanocrystalline phases, nanocrystalline structures. So, micro and nano are something which can be viewed by microscopy, and they have very profound impact on the properties of materials. Fourth is atomic structure. This atomic structure is something which is innate to materials. Materials tend to adopt atomic structure based on the bonding and based on energy calculations, as I showed you that atoms have to have certain equilibrium distance. So, based on the energetics, they tend to adopt certain configurations which determine their properties. So, what we will do next is we will go backwards. We will start looking from the atomic structure and then go to nano, then go to micro and nano structures. So, but before we go to atomic structures, let us just get into bonding. We were looking at it last time and we defined a term called as bond energy, which is the energy of the bonds corresponding to. So, if you have a plot like that, so this is the separation distance R, this is the energy E, and energy corresponding to the separation distance at which energy is minimum. This is the bond energy of the materials. And this bond energy has profound correlation with the properties, basic properties of materials. So, let me now get into the bonding. There are three kinds of bondings that we primarily come across or study. First is ionic bonding, second is covalent bonding, and third is metallic bonding. And then there is something, so these are all primary bonding methods, okay. So, this is called as primary. Then there is another class of bonding which is called as secondary bonding. And the reason for this classification is because primary bonding is typically characterized by high bond energy, high to moderate bond energy, high to moderate bond energy, and secondary bonding is characterized by low bond energy. So, I will show you the bond energy magnitudes later on as we move on, but there is a substantial difference between the bond energy of two things, and that is why materials which are purely covalently or ionically or metallically bonded, they are stronger than materials which are secondary bonded. So, let us look at the ionic bonding to begin with. Okay. So, ionic bonding happens when two elements have large differences in their electronegativities. So, for example, you take example of sodium and you take example of chlorine. Sodium has one extra electron in its outer shell, okay. Chlorine has 7, and 7. So, to complete its 8 electrons, it borrows 1 electron from this side. So, that sodium becomes stable, chlorine becomes stable, and the bond formed between two of them is called as ionic bond. And let me just tell you the energies of the values of electronegativity. So, chi of sodium has a value of about 0.9 and chi of chlorine has a value of roughly 3. So, this difference is substantial difference between the two, and this is related to the bond energy. So, and that is why ionic bonds are typically very strong. So, if you have, so other examples of these materials could be any, so you have magnesium oxide which is an ionically bonded solid, you have calcium fluoride, you have cesium chloride, you have calcium oxide, variety of these materials, they are all ionically bonded materials, and that is why they have they tend to have high strength, high melting point. So, basically I would say here high bond energy implies in this case high melting point, high elastic modulus, low coefficient of thermal expansion, and most ionic solids as a result have these characteristics. Then you have, we will go into details of ionic bonding a little later when we study the ionically bonded material structures. So, I am not doing mathematical treatment right now, I am just giving you a qualitative treatment at this stage. And then second is covalent bonding. So, for example, you take silicon, okay. Silicon has how many unpaired electrons? 4. So, silicon tends to share its electrons with neighboring silicon atoms. So, this is not give and take, this is sharing. So, neighboring silicon will have 1 electron here, they will pair. Similarly, this silicon will have 1 electron here, they will pair. This will have 1 electron here, it will pair. And likewise, this silicon on the outside will also be pairing with 4 neighbors. Okay. So, as a result, silicon has a 4-fold coordination. So, it pairs up every silicon atom in the silicon lattice is in the silicon structure is paired up with 4 silicon atoms, it has 4 neighbors, so as to have this covalent bonding, and this is called as. And so, not only silicon, but there are a lot of other elements which have this kind of characteristics. So, silicon is one, carbon, basically diamond has this kind of structure, silicon carbide, zinc oxide, which is an oxide which is partially ionic, but it also has a very strong covalent character. So, all these materials, they are covalently bonded. Gases such as Cl2, Br2, F2, all of them tends to be covalently bonded. Group 4 element, so in terms of materials, group 4, group 3,5 semiconductors and group 2,6 semiconductors, they tend to have very strong covalent character. So, these two also have ionic character, but they are partially ionic and covalent. So, these materials like silicon oxide, zinc oxide, silicon carbide and zinc oxide, they have quite strong covalent character. Again, they have similar characteristics, they have high bond energy. A covalent bond typically is characterized by high bond energy. As a result, covalent materials also have similar characteristics. Covalently bonded solids have high Tm, high E, which is basically elastic modulus, and low alpha coefficient of thermal expansion. Okay, I will also write in the previous slide Tm, E and alpha. Alright, so and the third bonding which is there, which is of primary nature, is called as metallic bonding, and most metals have this kind of bonding present. In fact all metals are bonded with metallic bonding. So, what you have here is basically, suppose this is a volume in which atoms are there, these are all atoms. So, positive core atom are left behind, and these are surrounded by this zillions of electrons, which are basically the valence unpaired electrons. So, this is, you can say, a sea of free electrons. And because this is a sea of free electrons, there is no as such like ionic or covalent kind of bonding. The bonding is, the bond energy is the E metals, let us say I write it as EB. Okay. Bond energy of metals is lower than typically EB ionic or covalent. It is not always true, but in most cases it is true. Metals have lower bond energy as compared to ceramics, which are ionically and covalently bonded, but metallic bond is fairly strong, still it is not very weak, it is very strong as compared to secondary bond, and this is typically bonding in metals and their alloys. Okay, so now the other kind of bonding that we discussed was called as secondary bonding. This is basically weaker than the primary bonds, and this basically arises from interaction between charged dipoles on the surface. As a result, so for example, you can have things like, let's say you have something situation like this, where so normally what happens is that center of negative and center of positive charges will coincide, but let's say you have a center of positive charge here and center of negative charge here, and similarly you have a neighbor which also has similar kind of configuration, center of positive charge here, center of negative charges here. These two attract each other, they form what is called as a secondary bond. Okay. So, this is because of asymmetric, let us say asymmetric charge distribution, and that is when you have asymmetric charge distribution, you will have formation of electric charge dipoles. Okay. So, this happens in things like hydrogen. Most of the gases have this kind of van der Waals kind of a structure because they have very weak water molecules are secondary bonded. Then second type could be you have present, for example, in polymers, you have these polymer chains. Okay. So, let us say these are all polyethylene chains. Okay. So, basically C2H4N. Okay. So, these chains are all covalently bonded. So, within chain you have covalent bonding, but between the chains the interaction is van der Waals. So, since in polymer chains are randomly oriented, that is why polymer is a little malleable, because the interaction between chains is very weak. So, this is for example, so this could happen because if you have, these chains will have branching, the groups will be present. Similarly, you have groups present here, there is some interaction between these groups on both sides, and again that is secondary in nature. This happens in polymers, things like HCl. So, many organic compounds have this kind of behavior. So, this is basically and this could be because of permanent dipole moment. So, materials which can have so things like water, things like various polymers, PTFE, PVDF. PVDF is a material with permanent dipole moment, still it is a polymer. So, you can also have examples are PVDF, or you can have PVC. Some of them may have permanent moment, some of them may not have permanent moment, but still you will have this secondary bonding. So, now let me come to some energies. So, for example, let me compare some compounds like you have lithium fluoride. So, lithium is from top of the periodic table on the left, fluoride is right on the right side. Then you have sodium chloride. Then let me take example of magnesium oxide. Then let me take example of calcium fluoride, and then let us take example of Al2O3. Now, you will see that now this bond energy is related to enthalpy of atomization, let us say. So, if I take the values, this is for example 864 kilojoule per mole. On the other hand, the value for NaCl is 640 kilojoule per mole. On the other hand, magnesium oxide has a value which is 1000, calcium fluoride has a value of 1548, and aluminum oxide has a value of 3060. These values can be found in any standard text, for example Raghavan by materials. Now, which of these you expect to have highest melting point, and which of these you expect to have the lowest melting point? So, as you have suggested, Al2O3 will have highest melting point. So, its melting point is 2050 degrees centigrade. So, let us say this is Tm and this is delta H, basically the enthalpy of atomization, which is nothing but related to bond energy. So, and NaCl by this token should have the lowest melting point. Its melting point is 801 degrees centigrade. Lithium fluoride has a 850 degrees centigrade. MgO has 2850 degrees centigrade and calcium fluoride has 1420 degrees centigrade. There are some exceptions in the middle, but by and large this rule follows. There are a lot of other reasons. You see, the melting point is related to the atoms themselves, the behavior of character of atoms. So, bond energy is one important factor, but by and large this is true. With the exception of calcium fluoride here, you can see that as you increase the bond energy, the melting point increases, and this is true about melting point, boiling point, and similarly you will have a decrease in the coefficient thermal expansion. So, if I now compare the fourth group elements, let us say group 4 elements. In group 4 elements, we have carbon, we have silicon, we have germanium, and we have grey tin, okay, tin. And if I look at the bond energy, diamond has 347 kilojoule per mole, silicon has 176, germanium has 159, and tin has 146. And I compare this with another material, which is silicon carbide, which has 308. And if you look at the values of melting point, diamond is about 3500 degrees centigrade plus, okay. It is difficult to measure the diamond's melting point because it is too high. Silicon has 1410 degrees centigrade, this has 937 degrees centigrade, this has 232 degrees centigrade, and this has about 2500 degree centigrade. So, you can again see the compounds which have lower bond energy, they have lower melting point, and this is true if you compare the values with these as well. So, of course, you can see that the bond energy, so this is enthalpy of atomization, not exactly the bond energy is related to that, but the sequence is the trend is fairly similar. What you get there is also true here. If I look at certain metals, for example, do not compare the values of two compounds directly, because that may not be very comparable directly, but let us compare some metals such as copper, let us say gold, let us say aluminum. I am just going to talk about the engineering metals, okay, nickel, zinc, tungsten and iron, okay. I am going to stop here. So, copper has a bond energy of 56.4 kilojoule per mole, gold has a value of 60, aluminum has a value of 54, nickel has a value of 71.6, zinc has a value of 21.9, tungsten has a value of 212.3, and iron has a value of 104. And by our experience we know which has highest melting point of these. So, tungsten has highest melting point of these, its melting point is 3410 degrees centigrade, which is very high. Iron, of course, you know that it is 1535 degrees centigrade. Aluminum, we know it is 667 degrees centigrade, copper is 1083 degrees centigrade, and gold is 1063 degrees centigrade. Nickel is again high bond energy, its melting point is 1453 degrees centigrade, and zinc of course is very low, it is 420 degrees centigrade. So, you can see again the correlation. These are all moderate bond energy metals, okay. The melting point is about 1000 or lower, aluminum is on slightly lower side, nickel, iron, they are on higher side, they have moderate melting points. zinc is of course very low. So, this is moderate, this is high, this is very high. Now, of course, if you compare with ceramics, if you, for example, if you compare with diamond, diamond has a bond energy of 347, and if you compare tungsten, tungsten has a value of 212, and they have similar melting points. So, bond energies for different classes of materials are not exactly comparable, because they have a lot of other factors to go behind, but by and large for the same category of materials there is a trend that as the bond energy increases, the melting point increases, and this is also true about the boiling point. Okay. This is how it will. So, to summarize this part, I would say I would write three kinds of bondings: ionic, covalent, metallic, and secondary. Okay. And let us first talk about the bond energy. Okay. EB. So, EB for ionic bond is typically large. Okay. EB for covalent bonding is variable, because for something like bismuth or tin it can be low. So, for tin, bismuth it is low, but for diamond it is high. For ionic bond it is typically large, but there are some compounds like NaCl for which it is not very high. Metallic bonding, it is variable again, low, moderate, high. Okay. So, low will be things like zinc, lead, moderate will be for things like copper, and high will be for things like tungsten. Okay. So, of course, defining the boundaries is not very easy, and secondary bonding is very small. It will have a bond energy which will be less than 10 kilojoules per mole. So, typically it is less than 5 to 10 kilojoule per mole. In fact, it is even lower than that. So, ionic we are looking at typically values greater than 100. Covalent we are looking at values which are between 50 to let us say 350. Metallic again will be anywhere from 20 to 350, and these will be very low, okay, less than 10. Of course, less than 10, but typically on the lower side they would be less than 1 kilojoule per mole. And another thing that you want to know is the nature. Now, ionic bond typically is non-directional. Okay. It does not have particular directionality. On the other hand, covalent bond is very directional. So, if you look at silicon, for example, silicon, this is central silicon atom, it is bonded by 4 silicon atoms. These silicon atoms are also bonded by 4 silicon atoms. So, as a result of maintaining this 4 bonds, it has to follow a certain geometrical framework, and that is why covalent bonds tends to be very because it requires sharing, it has to be very direct, it is very directional in nature. So, this is silicon or carbon, for example, silicon or carbon. So, this is directional in nature. Typically this you will see in ceramics, or this could be semiconductors also as well as ceramics. Metals of course is non-directional, and because of this moderate bond energy, that is why metals are ductile also. If bond energy was very high, they will not be deforming very easily. So, most metals are moderate or low bond energy, that is why they deform easily, and this is basically secondary bonding tends to be in polymers, for example, it is directional because it is between the chains. Okay. So, that is why it is directional, or it could be intermolecular as well. All right. So, some properties, of course, you know, bond energy. I have told you that bond energy has it has correlation with Tm, it has correlation with the modulus of elasticity, and it has correlation with alpha. So, I do not need to repeat this. This you have already been told. So, we will finish this part here and we will move on to the next part.